So, my name is Christoph Jenzen, and I would like to give a short introduction to spiking associative memory. So, let us start with associative memory. What we want is not the classical memory like in your notebook. You have a listing memory, so your things are encoded in a binary code and you put it in a list. If we have a large list of questions and answers, we have to search for our answers. That could take some time. What we want is a mapping memory. So we have input vectors and output vectors, and we want a simple matrix or something like this, which simply maps the questions to the answers. How is this realized on a neural network? These boxes are somehow the neurons. We have the neuron weights, and every neuron is connected to every input. We sum over all the input with connected with the weights. At the end, we have some sort of threshold, and we get our output. The weights have to be trained accordingly to input and output patterns, and to get a reasonable capacity, we have to have sparse patterns in the input and in the output. To get a better idea, we will restrict us to binary vectors. So here you see the trained images, which we can put into our associative memory. And what we can do then is to give a noisy version of those images. And the associative memory can recover the original images from the beginning. This looks, how does one do this? If we have only ones and zeros and we have two input vectors, we always have a 1 in the weight matrix if there's a 1 in the input and in the output. So that's how these ones here in the weight matrix are computed. And if we have the threshold set to 2 in this example, so we multiply this vector on the matrix and divide by 2, we get a 1 at the correct points. If we try to store additional vectors, we would like to get additional ones which are false, and that is why we need the condition that those vectors are sparse. I said something about spiking networks, so the next step is to do this with linear integrated fire or adaptive exponential integrated fire models, and therefore we have time as a new parameter. In our BNAM, so the binary version, we encode a 1 by a spike train so that we can recover losses without any problems. Another problem which we face is that instead of a single input, which is instantly fed to all neurons, we have a stream of input and a stream of output, and we have to recover which output belongs to which input. And all in all, we get also some additional input errors like offsets and jitter in the spike timings. And if we implement that on an analog hardware, we have to also deal with noise in neuron parameters and the state variable. So that was a bit fast. If you are interested into the topic, we see us this afternoon.